Hi, in this video, we're going to talk about the addition of alkenes of halogens. This is a process called halogenation. So if you have an alkene and you have a halogen-halogen bond, this could be chlorine or bromine, you will find the product ends up having two halogens attached to this molecule in an interesting orientation, and let's look at how this occurs. So just like when the alkene is reacting with HCl or HBr, the alkene acts as a nucleophile, and in this case, instead of reacting with a proton, it is reacting with the halogen, which breaks the weak halogen-halogen bond. And so you have this halogen exiting as a leaving group. But unlike protons, this halogen has other electrons, and so it kind of attacks back or reacts back with the resulting cation that's forming on the alkene, and this gives you a really special species. This is called a halonium ion. It's often a bromonium in the case of bromine, or a chloronium, but really bromonium is the most common of these halonium ions. I want to draw your attention to the fact that it is very similar in terms of structure to this protonated epoxide. You have this three-membered ring with a positive charge, and the reactivity of these halonium ions is very similar to the reactivity of protonated epoxides. So knowing that, we can take the X minus, the halogen with a negative charge that was the leaving group, and now use it as a nucleophile to break this carbon-halogen bond. And you'll note that it occurs from the opposite face of this halonium. So the two X groups wind up trans to each other, or again, on opposite faces of the molecule. So often when we're looking at these types of reactions, we look at them on rings so we can see evidence of the fact that the two halogens wound up on different sides of the molecule. Again, I want to highlight that the two halogens that we'll use in this case are bromine, Br2, and chlorine, Cl2. So again, I mentioned before that we like to use rings, and sure enough, here's a ring to help us keep track of the atoms. In this case, we're going to have a more substituted and a less substituted carbon, and let's see how these react. So here are the products. So you have one product and an enantiomer, and again, the two halogen atoms wind up on opposite faces. But let's see which one came in first. That's the big question here. So if we attack, or if you use the nucleophile, the alkene as a nucleophile and react with this bromine atom, that you have this other purple bromine atom as a leaving group, the electrons from that first bromine come back and form this three-membered ring, this bromonium ion. It's important to recognize that a bromide is a pretty weak nucleophile, and so we're going to use the same logic we did in the protonated epoxide case, where this positive charge is actually shared across these carbon atoms, and one of these carbon atoms has kind of a bigger delta positive or more positive character. And that's exactly where the bromide is going to react. So it's going to react in a contrasteric fashion. It's going to react where the more positive character is built up. So that means that if we're keeping track of it, the first bromine atom that was added to the molecule ends up being this one away from the more congested center, and the second one came in here at the more stable, the center where there will be a more stable cationic charge. Let's look at another example. So if we now look at this where this alkene has equal substitution, but there is a steric blockade up here in the form of an isopropyl group, we can look at how this will react with bromine. So if this alkene were to react with bromine, there are two possible bromonium ions that could form. One of them with the bromonium ion on the same face of the isopropyl, and one of them with the bromonium ion, or the bromine atom, on the opposite face. So the opposite face is desirable because there is a steric interaction between this isopropyl and this bromonium ion. So this is going to be the desired intermediate that you'd form. So now this bromide as a nucleophile has two choices, and electronically these two choices are the same. Again, we don't have a bigger delta positive on either of these two carbon atoms because they have equal substitution. So now the argument is truly steric. remember that this bromide has to approach from the opposite face of this bromonium ion. The opposite face, in this case, happens to have an isopropyl on it. So one of these two faces is blocked sterically by this isopropyl, which means this second bromide ion is going to come in from the least sterically blocked face, which would result in this particular dibromide as the resulting product. So let's look at the case when you have a bromine atom, halogenation, when you have a solvent that can also participate in the reaction. So just like before, we would form the bromonium ion first, and mechanistically this is going to happen just like you saw on the previous pages. Unlike the previous pages, there's another nucleophile present. In this case, water can act as a nucleophile, and it will react with the more substituted carbon atom, again because water is a weak nucleophile in this case, and it will crack open the three-membered ring to give you this, protonated water and this halogen. Note, again, they are on opposite faces of this molecule. It's really important to recognize the anti relationship to each other. So we don't like to leave our molecules in the protonated form like this, so we could show there's other water around that can pick up the proton and give us our final product, which has an alcohol directly adjacent to this bromide leaving group. I'll point out that if you deprotonated this alcohol, you could form an epoxide because the leaving group is anti-periplanar to this nucleophile. If you did this reaction in the presence of methanol instead of water, a very similar argument would happen, where you would have this bromonium ion formed, and then methanol would intercept the bromonium ion in the same way that water did, and eventually result in a product where you form this methyl ether with this halogen. And again, they're on opposite faces of each other. I'd like to point out one final time that in every one of these cases, the very first face that I approached with this bromine atom, in this case, there is no stereogenic carbon on this ring. And so both of these faces are equal, meaning that in all of these cases, you would also observe the enantiomer. So that's the exact opposite stereochemistry of these two species, but the same connectivity. So again, the bromide would be connected to this carbon atom. The oxygen would be connected to this carbon atom. They'd simply have their wedges and hashes switched. Thank you for your time, and I look forward to your questions.